Every advanced chip powering AI, smartphones, and modern data centers depends on a machine that only one company in the world can currently produce at scale. Dutch giant ASML builds these systems at cost exceeding $350 million each, using technology so extreme it creates plasma hotter than the surface of the sun to produce light that even air can absorb. Now China may be challenging that monopoly, and the semiconductor industry is watching closely. Now let us get into what actually happened, because the real story is far more layered than the headlines suggest. The machine that rules the world. To understand why this matters, you first need to understand what ASML actually does, because the complexity of its machines is not a talking point. It is the entire reason a monopoly this absolute has been allowed to exist for decades. An extreme ultraviolet lithography machine, or EUV, works by firing a high-powered carbon dioxide laser at tiny droplets of molten tin, each about 25 micrometers in diameter, roughly 1/3 the width of a human hair. These droplets are ejected from a generator at a speed of 70 meters per second. The laser hits each droplet twice. The first pulse flattens it into a pancake shape. The second, far more powerful pulse vaporizes the flattened tin and creates a superheated plasma that reaches roughly 250,000 degrees Celsius. That plasma emits a burst of extreme ultraviolet light at a wavelength of 13.5 nanometers, about the width of 5 DNA strands. This sequence happens 50,000 times every single second, around the clock. But generating the light is only the beginning of the problem. EUV light is absorbed by every known substance, including glass and air. That means the entire optical system must operate in a high vacuum. You cannot use traditional lenses because the light would never pass through them. Instead, ASML uses mirrors, manufactured by the German optics company Carl Zeiss, that are the flattest reflective surfaces ever produced. If one of these mirrors were scaled up to the size of Germany, the largest bump on its surface would be less than a millimeter tall. Even with that level of precision, each mirror reflects only about 70% of the light that hits it. After the roughly 11 reflections needed to guide the beam from source to wafer, only a small fraction of the original energy actually arrives at the silicon. Every component in the machine is engineered around that constraint. To put the precision in terms that are easier to grasp, ASML's own engineers have compared the targeting accuracy to standing on Earth and shining a flashlight at the moon and hitting a coin. That is the level of control required, and it must be sustained continuously for production runs that last thousands of hours. The newest generation of these machines, the high-NA EUV systems with a numerical aperture of 0.55, cost roughly $400 million each and can print features at 8 nanometer resolution. Each one ships in roughly 40 freight containers and takes months to install and calibrate inside a customer's fab. ASML did not build this alone. The foundational research behind EUV lithography began at 3 United States Department of Energy national laboratories, Lawrence Livermore, Sandia, and Lawrence Berkeley, under a program funded from 1997 by an Intel-led industry consortium. ASML joined the consortium in 1999 and in 2001 acquired Silicon Valley Group, the last American lithography manufacturer, for roughly $1.6 billion. By 2012, the cost of developing EUV had grown so large that ASML's 3 biggest customers, Intel, TSMC, and Samsung, directly invested in the company, buying a combined 23% stake to keep the program alive. That co-investment also funded ASML's $2.5 billion acquisition of its light source supplier, Cymer. That co-investment was not charity, it was survival. Without it, the EUV program would have run out of money before it reached commercial viability, and the entire semiconductor roadmap below 7 nanometers would have stalled. The result is a machine that took 3 decades, over 5,100 suppliers across multiple continents, and billions in shared investment to bring to commercial production. In 2025, ASML delivered 48 EUV systems within total sales of 32.7 billion euros. It holds nearly 5,000 lithography-related patents. No other company on Earth can build what it builds. That is not a market advantage. It is a technological moat so deep that entire nations have tried and failed to cross it. What China actually built. On July 27, 2026, the information reported that a state-backed Shanghai company had begun mass-producing immersion deep ultraviolet lithography machines and planned to deliver the first units to China's leading chipmakers before the end of the year. Reuters confirmed the report the following day and, for the first time, named the manufacturer, Shanghai Aishengna Electronic Technology Group. The company had no public website. It had disclosed nothing about its operations. What it did have was talent. Aishengna had quietly absorbed engineering teams from lithography startup Shanghai Ultraviolet Technology, an affiliate of Huawei-backed equipment maker Sea Carrier, and from Shanghai Microelectronics Equipment, known as SME. Corporate and recruitment records showed that Aishengna and Ultraviolet shared a Shanghai address. Aishengna's parent company is Shanghai Electric, which is also the parent of SME. When SME was restructured in 2024, the lithography work was divided across 3 entities. SME retained responsibility for older KRF and I-line systems. A spin-off called AIMES handles back-end lithography equipment. Aishengna, established in August 2023 with registered capital of roughly $1 billion, took on the most advanced work, Immersion DUV. The entire operation was a national team effort assembled from the players China had spent years building under export pressure. Now the critical distinction. Aishengna is not building EUV machines. It is building immersion DUV machines, deep ultraviolet. This is an older generation of lithography technology that uses 193 nanometer light passed through a layer of ultra-pure water between the lens and the wafer, which increases the numerical aperture and improves resolution. In a single exposure, Immersion DUV can print features at the 28 nanometer scale. Through a technique called multi-patterning, where the same wafer is exposed multiple times with precisely aligned patterns, DUV machines can be pushed to produce chips at the 7 nanometer class. This is not theoretical. SMIC, China's largest foundry, already produces 7 nanometer chips using older ASML DUV tools. What the domestic machine adds is not new capability. It adds a domestic supply path for capability China already has, one that cannot be severed by a policy decision in Washington or The Hague. SMIC has been evaluating a Yuliangsheng immersion DUV system since September 2025. The initial production targets are modest, roughly 5 machines in 2026 and around 20 in 2027. For comparison, ASML shipped 131 immersion DUV systems in 2025 alone and plans to increase capacity by 30% in each of the next 2 years. The overall count of ASML immersion DUV systems deployed worldwide likely exceeds 1,400, so the output gap is enormous. But the significance of the moment is not about volume, it is about the direction. Why this scares the market more than the numbers suggest. 5 machines against ASML's 131 looks like a rounding error. JP Morgan told investors the sell-off seemed disproportionate, and in pure production terms, it is. But the market was not pricing the machines China built this year. It was pricing what those machines represent over the next decade. The initial market logic was brutal. If Chinese engineering had conquered the immersion DUV bottleneck, the reasoning went, then the rest of the semiconductor equipment supply chain, deposition, etching, inspection, was vulnerable to the same treatment. The fear triggered a synchronized sell-off across the entire sector. ASML, Applied Materials, Lam Research, and KLA were all down roughly 7% at their intraday lows, wiping out tens of billions in market value in a matter of hours. ASML's July 2026 decline ultimately reached 18% for the month. It's worse since mid-2024, even though the company had just raised its full-year revenue guidance for the second time that year and posted quarterly earnings above analyst expectations. Consider the context. From 2023 to 2025, Chinese companies purchased roughly 230 immersion DUV lithography systems from ASML. China represented around 33% of ASML's net sales in 2025, a figure that has since dropped to roughly 20% in 2026 as export restrictions tightened. Meanwhile, the United States Congress is advancing the Match Act, legislation that would block ASML from selling or servicing DUV machines for the exact 3 Chinese fabs set to receive Aishengna's domestic tools: SMIC, Huahong, and Changshin Memory Technologies. If that legislation passes and China can simultaneously build its own machines, then the restrictions lose their strategic purpose entirely. The lever Washington has spent years constructing would be pulling on nothing. This is the strategic paradox at the heart of export controls. The restrictions were designed to keep China dependent on Western equipment. Instead, they gave China exactly the motivation it needed to fund domestic alternatives at a scale that would never have been politically justifiable without the threat of being cut off. Every tightening of the controls accelerated the very outcome they were meant to prevent. Analysts at Semi-Analysis cautioned that tool performance, scaling production, fleet reliability, the surrounding ecosystem, and poor economics against fully depreciated ASML machines all stack up against China's DUV effort. They noted that scaling production of the machine itself is the most underestimated part. That is correct, but it is also exactly the argument people made about China's ability to build 7-nanometer chips at all, right before SMIC proved it could. The other front nobody expected. While the DUV story dominated headlines in July 2026, a parallel program had already been underway for years, operating under a level of secrecy that took the intelligence community by surprise when Reuters revealed it in December 2025. In a high-security laboratory in Shenzhen, a team of Chinese scientists had built a prototype EUV lithography machine. The prototype was completed in early 2025 and was undergoing testing at the time of the report. It filled nearly an entire factory floor, far larger and heavier than ASML's 180-ton production EUV system. The oversized design was intentional, built to maximize light output at this early stage, rather than to optimize for commercial form factor. The team behind it included former ASML engineers who had been recruited as part of an aggressive talent drive launched in 2019. These recruits were offered signing bonuses between 3 and 5 million yuan, roughly $420,000 to $700,000, along with housing purchase subsidies. Among them was Lin Nan, ASML's former head of light source technology, who is now a professor at Beihang University. His team at the Chinese Academy of Sciences Shanghai Institute of Optics filed 8 EUV light source patents in just 18 months. The recruits reportedly operated under aliases. Cameras monitored their workstations to record the disassembly and reassembly of components. Sources said older ASML components acquired through secondary markets helped the team build this first domestic machine. People familiar with the work compared the entire effort to China's Manhattan Project, a nationally coordinated push ordered by Xi Jinping, who had made semiconductor self-sufficiency a top priority. State media identified Ding Xuexiang as the official overseeing the broader semiconductor strategy. Huawei was described as playing a central coordinating role, linking a web of companies and state research institutes across the country involving thousands of engineers. The Shenzhen project stayed classified even as Beijing spoke publicly about other chip ambitions. Approximately 100 young Chinese engineers were assigned to the facility, tasked with reverse engineering components from both EUV and DUV machines. Employees reportedly receive performance bonuses for successfully reproducing individual parts. The prototype is operational. It can generate EUV light. it has not yet produced functional chips. Beijing has set an official target of 2028 for chip production on the prototype. Sources close to the project believe 2030 is more realistic. The gap that still exists is just as important as the achievement itself. It is important to state clearly what China has achieved and what it has not. The EUV prototype is a proof of concept, not a production-ready lithography tool, and that distinction is enormous. Generating EUV light under controlled laboratory conditions is one problem. Turning that light into a reliable manufacturing process capable of producing advanced chips at commercial volume, with high yields and repeatable performance, is an entirely different challenge. The distance between those 2 points is enormous. It took ASML roughly from 2006 to 2019 to move through that development process, and ASML had decades of accumulated engineering knowledge, an exceptionally sophisticated global optical supply chain, and financial backing from virtually every major chipmaker on Earth. China is therefore not starting from the same position, even if the prototype demonstrates that meaningful progress has been made. The breakthrough matters, but the hardest part may still be turning the laboratory achievement into a machine that can run reliably inside a high-volume semiconductor fab. 2 teams are currently working on EUV light sources in China. Lin Nan's group has a solid-state laser-produced plasma design running at 3.42% conversion efficiency. Commercial viability requires approximately 5.5%. Zhao Yongpeng's team at Harbin Institute of Technology has reached around 100 watts of EUV output. ASML's production sources deliver roughly 600 watts. In 2024, ASML's CEO suggested China was 10 to 15 years behind in EUV. In March 2026, semi-analysis analyst Dylan Patel predicted fully indigenous DUV tools and pre-commercial EUV tools by 2030. On the DUV side, the gap is real but narrower. Chinese commentators have noted that Aishengna's 28-nanometer DUV machine is roughly equivalent to ASML's product from about 15 years ago, placing it approximately 4 generations behind in performance. But as one Liaoning-based columnist put it, China has at least achieved a key breakthrough from 0 to 1 in the mature process node segment. The country plans to invest heavily in 3 areas to close the remaining gap: high-power DUV light sources, high-precision 193-nanometer optical lenses, and synchronization control algorithms. These are the specific subsystems where performance differences between ASML's machines and China's show up most acutely in production. Overlay accuracy, throughput, defect rates, yield consistency, and reliability over long production runs are all areas where the domestic tools remain unproven at scale. And then there is the component problem. Many of the critical parts required to build these machines are still imported from Japan, which means domestic assembly does not automatically translate into true supply chain independence. Delays from local suppliers were one of the factors that capped 2026 output at around 5 units, highlighting just how difficult it is to scale a machine this complex. A system can be designed and assembled domestically, while still depending on foreign suppliers for the precision components that determine whether it can actually operate. That creates a vulnerability at exactly the point where the project is supposed to eliminate one. The machine may be domestically assembled, but it is not yet fully domestically sourced, and that distinction matters enormously because supply chain independence was the entire strategic objective. Until those imported components can be replaced with reliable domestic alternatives and produced at sufficient volume, the achievement is impressive but incomplete. Why the direction matters more than the distance. The instinct when evaluating China's lithography push is to measure the gap against ASML's current position and conclude that China is too far behind for any of this to matter in the near term. That analysis is correct on the specifics and wrong on the trajectory. Aishengna's production pace of 5 Immersion DUV machines in 2026 and an expected 20 in 2027 is consistent with the rate at which ASML itself scaled its own immersion DUV production during the 2003 to 2005 validation phase, when ASML deployed 13 immersion machines for commercial validation. The starting point is modest. The pattern is not unprecedented. Meanwhile, China's broader semiconductor equipment ecosystem is growing at a pace that compounds the significance of any single breakthrough. Naura Technology, a Chinese chip equipment manufacturer, became the world's fifth largest by 2025 sales, trailing only ASML, Applied Materials, Lam Research, and Tokyo Electron, and moving ahead of KLA for the first time. Naura booked the equivalent of $4 billion in revenue in the first 3 quarters of 2025 alone, up from roughly $589 million for all of 2020. It holds an order backlog stretching into 2027 and has now begun developing lithography tools for the first time. AMEC, another Chinese equipment maker, grew revenue and net profit by more than 30% in 2025. ACM Research, which specializes in cleaning equipment, posted $901 million for fiscal 2025 and guided to as much as $1.18 billion for 2026. The ecosystem around the machines is filling in: etching, deposition, cleaning, inspection. China is building domestic capability across the entire semiconductor equipment stack, not just in lithography. The DUV machine is the headline. The supply chain beneath it is the story. China is also pursuing alternative paths that bypass lithography constraints entirely. Huawei is reportedly preparing advanced packaging and chiplet architectures that assemble multiple smaller dies into a single high-performance package, reducing the need for the most advanced single-die lithography. Separately, Chinese companies are exploring glass substrates as a way to improve processor density and thermal performance without depending on restricted EUV machines. A Chinese startup has even claimed it can produce photonic chips using nano-imprint lithography rather than DUV, a process it says cuts costs by 90%. These are parallel bets, each one attacking the bottleneck from a different angle. Changshin Memory Technologies, one of Aishengna's 3 named customers, is expected to expand monthly wafer capacity to around 350,000 wafer starts by the end of 2026, putting the company within striking distance of Micron's production scale. That makes the availability of domestic lithography equipment far more than a question of technological pride. CXMT does not have access to EUV, so its advanced DRAM development depends heavily on immersion DUV combined with increasingly sophisticated multi-patterning techniques. Every additional process layer and patterning step adds complexity, cost, and opportunities for defects, making reliable access to lithography equipment critical to keeping production moving. For CXMT, a domestic DUV supply chain is therefore not simply a convenient alternative to foreign equipment. It could be the difference between continuing to scale advanced memory production and eventually running into an equipment bottleneck imposed by export restrictions. If domestic suppliers can provide the necessary tools at sufficient performance and volume, CXMT has a path to keep expanding without depending on foreign lithography systems. What has to go right? China's DUV tools need to prove they can run in a high-volume production environment over thousands of hours without degrading in overlay accuracy or throughput. Building a machine that works is one problem. Building a machine that works identically on the 10,000th wafer as it did on the first is a different problem entirely, and it is the problem that separates prototype from product. The founders of SMIC and Chinese equipment maker AMEC have publicly urged Chinese fabs to test domestic chipmaking tools on active production lines, not just an isolated evaluation base, because real-world validation is the only way to close the reliability gap. That gap exists because ASML's machines benefit from decades of high-volume manufacturing data fed back into continuous refinement cycles, a feedback loop that no newcomer can shortcut. You cannot simulate 1,400 deployed machines worth of field data. You earn it one production hour at a time. The EUV prototype faces even steeper challenges before it can become anything resembling a commercial production machine. The conversion efficiency of its light source needs to nearly double, while the usable output power needs to increase by roughly 6 times to reach the levels required for high-volume manufacturing. Then there is the optical system. EUV lithography depends on mirrors manufactured to extraordinary levels of precision, a capability that Carl Zeiss currently provides at commercial scale, but which is not available to China through normal supply channels. And the optics are only one piece of the problem. The light source, mirrors, wafer stage, reticle handling system, vacuum environment, control electronics, and computational lithography software all have to operate together with extreme precision and reliability. At these scales, even microscopic errors can become manufacturing defects across an entire wafer. The tolerances involved are measured in picometers, approaching dimensions smaller than individual atoms. Getting one subsystem to work in isolation is difficult enough. Getting every subsystem to work together, continuously, thousands of times per hour, while maintaining commercial yields, is the real engineering challenge. ASML itself is not standing still. The company has demonstrated a 1,000-watt EUV light source in its lab, a milestone that would enable its systems to expose 330 wafers per hour, 50% more than current models. It is developing high-NA EUV with a numerical aperture of 0.55, enabling 8-nanometer single-exposure resolution for sub-2 nanometer chip nodes, with even more extreme Hyper-NA at 0.75 on the roadmap for the early 2030s. ASML's roadmap is a moving target, and it is moving faster than the company chasing it. None of these challenges change the fact that China has moved from zero to a functional domestic DUV production line and a working EUV prototype in roughly 6 years. The question is not whether China can match ASML today. The answer to that is clearly no. The question is whether the trajectory leads somewhere that fundamentally changes the global semiconductor map. And the answer to that depends on how you define the destination. What this actually changes. The framing that dominated the news cycle, that China has replaced ASML, is wrong. ASML remains the sole manufacturer of commercial EUV lithography systems. Its monopoly on the technology that prints every cutting-edge chip below 7 nanometers is intact. No Chinese tool has produced a single commercial chip at a node that requires EUV. But the framing that nothing has changed is equally wrong. For the first time, China has a domestic path to produce the lithography equipment it was told it could never build. The DUV machines being delivered to SMIC, Huahong, and CXMT this year represent something that cannot be sanctioned, cannot be embargoed, and cannot be switched off by a government on the other side of the world. Made in China 2025, Beijing's industrial policy framework called for domestic production of immersion DUV machines before 2025. Aishengna delivered roughly a year late. Measured against self-sufficiency, the goal Beijing actually prioritizes, the program is approximately on schedule. The semiconductor equipment industry has operated for decades on an assumption that certain technologies were simply too complex for any single nation to replicate without the cooperation of the existing global supply chain. EUV lithography was the ultimate proof of that assumption. It took 30 years, 3 continents, billions in co-investment, and the combined expertise of thousands of the world's best optical, mechanical, and plasma physicists to make it work. That assumption is not broken, but it is being tested in a way it has never been tested before, by a country that has shown repeatedly over the past decade that it treats technological blockades not as permanent barriers, but as engineering problems with very large budgets. ASML itself acknowledged the reality, if carefully. In a statement responding to the Reuters report on the Shenzhen EUV prototype, the company said it makes sense that companies would want to replicate its technology, but doing so is no small feat. That phrasing concedes the ambition while emphasizing the difficulty, which is exactly the right framing for a company that spent 30 years proving how hard this is. The question is whether 30 years of difficulty remains 30 years of difficulty when someone else can study the documented development pathway, recruit the engineers who built it, and deploy a national budget to compress the timeline. The machines China builds today are not the machines that will challenge ASML. The machines it builds in 2030 might be. And the strategic decisions being made right now by companies, by governments, by investors are all quietly adjusting to that possibility. Taiwan Semiconductor Manufacturing Company is building $165 billion worth of fabs on American soil, partly to insulate the West's chip supply from geopolitical disruption. Intel is restructuring its foundry business to compete for government subsidies. Japan and South Korea are tightening their own export controls on semiconductor materials. The entire global semiconductor architecture is being rewired in real time, and the catalyst is not a trade policy or a tariff schedule. It is a machine in Shanghai that did not exist 2 years ago. Turn on notifications so you never miss one, and tell me in the comments, if the most complex machine ever built was supposed to be impossible to replicate, what does it tell us about the next decade when someone builds a working version in 6 years? If this gave you something to think about, subscribe and see you in the next video.